So our claim is that the sequence ynm, which is defined as ynm is equal to actually gamma 1m x1 plus etc. gamma nm xn, which converges to y. Y is actually beta 1 x1 plus etc. beta n xn. Here clearly we can understand that we have already assumed that gamma 1m converges to beta 1. So gamma 1m x1 should converges to beta 1 x1. Clearly it is clear that. And gamma 2m, here it is gamma 2m x2 should converge to beta 2 x2. And similarly gamma nm xn should converge to beta n xn, because gamma nm converges to beta n, which we have already assumed. So it is clear that the sequence ynm should converge to y, the number y. Okay, so and we have already assumed that summation j is equal to 1 to n modulus of gamma jm should be equal to 1. So from that, summation j is equal to 1 to n modulus of beta j should always equal to 1. Okay, so which means that not all beta 1, beta 2, etc., beta n are 0. At least one of them should be not equal to 0. Okay. So at least one of them is not equal to 0 means this summation should not be equal to 0. Why is not equal to 0? Because x1, x2, etc., xn is assumed to be linearly independent. So it cannot be all 0. It cannot be contain 0 vector in general. And modulus of beta j summation is equal to 1, which means that all beta j, not all beta j are 0. If all beta j are 0, then its summation should always be equal to 0, which is not possible, which is equal to, given that it is equal to 1. So clear that not all beta j are equal to 0. So at least one of them is not equal to 0. And it is clear that x1, x2, etc., xn is linearly independent means all of the x1, x2, etc., xn are non-zero, which means that its summation, its linear combination should not be equal to 0. Okay, and which means that y is not equal. So y is not equal to 0, and it is assumed that it is given, we have already established that ynm converges to y, which implies by the continuity of norm ynm converges to what? Norm y. It is because the continuity of norm is continuous. Xn converges to x means norm xn converges to norm x. It is clear from the continuity of the norm. Okay. So now we know that ynm is a subsequence of ym, okay, which we have already established in the previous video. Here ynm is a subsequence of its previous one, it's a subsequence of previous one, etc. So y1m is a subsequence of ym, y2m is a subsequence of y1m, which means it's a subsequence of ym, etc. ynm is a subsequence of actually y1m if you proceed like this transitivity property, which means that ynm is a subsequence of ym. Okay, so ynm is a subsequence of ym, and we have already assumed that by our assumption ym should be converging to 0. If a sequence is converging to 0, all its subsequents should converge to the same limit. And a sequence and subsequence cannot have different limits. So a sequence converges to 0 means every subsequence of that sequence should converge to 0 as well. So ynm is a subsequence of ym, which means that ynm should be converging to 0 as well. Okay, or norm ym or norm ym should be tending to 0, which means that norm y nm should go to 0. Okay, since we already assumed that norm ynm should go to norm y and norm yn should go to 0, which means that norm y is equal to 0. Norm y is equal to 0 implies y is equal to 0 by the definition of norm. But we have already assumed that y cannot be equal to 0. But we have established that y is equal to 0. So our assumption should be somewhat wrong. Okay, so which means that our assumption is wrong. Assumption is wrong. So what was our assumption? We assumed that our result is not true. Okay, so which means that our result should be true. So this is how we prove this theorem. Okay, so I will restate the whole thing again. Okay, so what we have to do was, we are given with a linearly independent set of vectors. We should be finding a constant c, and for any given choice of scalars, this inequality should be holding. This is what we have to prove. And we choose this right hand side, the modulus the right hand side, as s. If s is equal to 0, the right hand side is equal to 0, and norm of anything is always greater than or equal to 0, which means the result is true when s is equal to 0. Now we assume that s is greater than 0, and we move this s from the right hand side onto the left hand side, and by the property of norm we can insert, because it's modulus, s is modulus of alpha 1 plus alpha 2 modulus of alpha 2 plus etc modulus of alpha, which is always greater than or equal to 0, which means that its modulus of s should be equal to s. You can insert the whole thing inside that. So we termed alpha I by s as beta I. So we can restate this as modulus of beta 1 x1 plus etc beta n xn greater than or equal to 0. So in order to prove our inequality for s greater than 0, it is enough to prove that modulus of beta 1 x1 plus etc modulus of beta n xn should be greater than or equal to c, where summation modulus of beta I is equal to 1. Okay. Now we assume that this result is not true. Okay, our assumption is true. Okay, which means that for any given beta 1 beta 2 etc beta n, and for any given positive constant c, this cannot be greater than c, it should be less than c. Okay, now our objective is, we find some sort of contradiction at some stage, so that our assumption of assuming this result is not true becomes wrong, which means that this result is true, which is what we are going to establish. So we assume that for any given constants beta 1 beta 2 etc beta n, and for any given c, this cannot be greater than c, because which implies that it should be less than or equal to c. And in particular, for it is true for any given set of constants, I choose a class of sequence, a class of such constants, and associated with that sequence I define this linear combination as a sequence ym. Okay, so this this means that it should be true for ym as well. So by our assumption, so norm of ym should be less than some epsilon. If you c should be some small positive number, which means the norm of ym minus 0 should be less than or equal to c, which means that ym should be tending to 0. So if you assume that this thing is less than c, then for any given set of constants, this linear combination, or the sequence which is interpreted as the linear combination, should go to 0 with this condition. This is what we assume. And now, so since this sum is 1, each of the terms should be less than 1, which means that the corresponding sequence, which is a real sequence, beta im, for I is equal to 1, 2, 3, etc. n, is actually a bounded sequence. And by Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence. Then beta im has a convergent subsequence for I is equal to 1, 2, 3, etc. n. In particular, I choose beta 1, which has a convergent subsequence. It has a convergent subsequence means it should converge to some particular number. That subsequence should converge to some particular number. Let that number be beta 1. Right? Now I define ym, the general term ym, and instead of beta 1, beta 2, etc., beta m, I took a subsequence. Okay, and associated with that the subsequence, we can take a subsequence of the sequence ym. Okay, let that subsequence be y1m. So y1m is actually a subsequence of ym, which is obtained by replacing beta 1 1, beta 1 2, etc., beta 1 3, etc., by its subsequence, which converges to beta. And similarly, in y1m, you can take beta 2m. Okay, and beta 2m is always bounded, and it has a convergence subsequence which converges to beta 2. Associated with that convergence subsequence, we can choose a subsequence of y1m and call that as y2m. So y2m is actually a subsequence of y1m. Y1m is a subsequence of ym, which means that y2m is a subsequence of ym. Okay, and if you proceed like this, ym has a subsequence y1m, which is obtained by replacing beta 1m by its convergence subsequence, and y1m has a convergence subsequence y2m, which is obtained by replacing beta 2m by its convergence subsequence. And if we proceed like this by replacing up until the nth stage beta nm by its convergence subsequence, we get at last a subsequence ynm, which can be termed as a subsequence of ym, which is defined as this. And okay, so here gamma 1n is actually a representation of the subsequence which is chosen from beta 1n. Gamma 2m is actually a representation of the sequence which we chosen from beta 2m, etc. Gamma nm is a representation of the sequence which is chosen from beta nm, which converges to gamma nm converges to beta n, etc. And its summation should be equal to 1 because this sum should be equal to 1. And now beta 1f has a subsequence gamma 1m which converges to beta 1. Beta 2m has a convergence subsequence gamma 2m which converges to beta 2, etc. Beta nm has a convergence subsequence gamma nm which converges to beta n. And associated with this, and we have a linearly independent set of vectors, we can define a linear combination y as beta 1 x1, beta 2 x2, etc., beta n xn. Now we can easily understood that the sequence ynm should go to y, converges to y, because ynm is defined as gamma 1m x1 plus etc. gamma nm xn. Here x1, x2, etc., xn are fixed vectors, so it does not vary at all. We have clearly understood that gamma 1m is converging to beta 1. So gamma 1m x1 should converge to beta 1 x1, and gamma 2m converges to beta 2. So gamma 2m x2 should converge to beta 2 x2, etc. Gamma nm should converge to beta n. So gamma nm xn should converge to beta n xn. So clearly from that linear combination of this should converge to beta 1 x1 plus etc. beta n xn, which is taken as y. With since summation j is equal to 1 to n modulus of gamma jm is equal to 1, its converging part should always, whose sum should always go to 1 as well. Okay, and now we can easily understood that since x1, x2, etc., xn are linearly independent, none of those vectors should be equal to 0. And since summation j is equal to 1 to n beta j is equal to 1, at least one of them should not be equal to 0, which means that its summation cannot be equal to 0. Okay. So y cannot be equal to 0. Ynm is converging to y, and by continuity of the norm, ynm should converge to norm y. So ynm is a subsequence of ym. We have already assumed that by our assumption, ym is a sequence which converges to 0, which means that norm ym converges to 0. And ynm converges to 0 means yn converges to 0 means every subsequence of yn should converge to 0 as well. So ynm is a particular subsequence of yn. So yn converges to 0 means its subsequence ynm converges to 0, which means that norm ynm should converge to 0. We have assumed that norm ynm converges to norm y, and norm ynm converges to 0 means norm y should be equal to 0. Norm y is equal to 0 means y equal to 0. We have assumed that from our assumption y cannot be equal to 0. Here we have obtained that y is equal to 0. So our assumption should be wrong. Well, our assumption that the result is not true, which was our assumption, that is beta 1 x1 plus etc. beta n xn should be less than c, which is not true. So it should be greater than or equal to c. So from which we can easily understand that this result is true. Okay, thank you.